Hi, everybody. Welcome back. Here's our next little mini lesson on respiratory system physiology. This topic is going to talk about gas transport. So in the prior video, we talked about internal and external respiration, the pickup and dropping off of oxygen and carbon dioxide, kind of following the Dalton's law of partial pressures and Henry's law of solubility of gases, and basically concentration gradients, things like to go from a high concentration to a low concentration. So now what we're going to talk about is once that gas is in the blood, how is it transferred from capillary bed to capillary bed, whether it's the CO2 being picked up at the peripheral tissues, heading to the lung capillary beds, or the oxygen being picked up at the lung capillary beds and dropped off at the peripheral tissue capillary beds. So what does it do in between that pickup and drop off? So that's what this little mini lesson will cover. All right, so again, here is our overview diagram. So we are going to be focusing on this part right here. So we're going to talk about oxygen transport first, and then we're going to take a look at how carbon dioxide is transported. Oxygen is definitely the more simpler of these two gases, and then CO2 is a little bit more complex. So we'll just kind of tackle it as we go. All right, so first looking at oxygen transport, this is what's called the hemoglobin saturation curve. So in this diagram, what you'll see is the relationship between the partial pressure of oxygen and at what percent is the hemoglobin saturated. So if you remember from blood chapter, you remember hemoglobin was kind of like this 4-part tertiary protein. It's a really bad drawing of hemoglobin. But if you remember in the middle, we had the hemes. We had two alpha units and 2 beta units. And so each one of those hemes was able to hook onto O2 gas. So when your hemoglobin is saturated, excuse me, each hemoglobin can hold 4 molecules of oxygen. So that's what we're talking about with saturation. So if you did the pulse oximeter back when we were still able to have class in our blood chapters, you may have seen that you were 99, 98, 99% saturated. That's what this is referring to. How many oxygen molecules are bound to each of your hemoglobin molecules. So if we kind of highlight our key points here, when our PO2 is at 100, and if you remember, was at 100 right at the pulmonary capillaries. So that's the concentration in the alveoli moved into that pulmonary capillary bed until it left the lung and the pulmonary vein as 100 partial pressure of oxygen. So then if we follow that up to about right here, we can see that 100% saturation, or sorry, 100 partial pressure is about 97.5, 98% saturated. So most of your hemoglobin is going to have almost all of its heme units bound to oxygen. So then if we go down to where oxygen was the lowest in our normal tissue situation, right? So the peripheral tissues, our tissues were at the level of 40 partial pressure, right? 40 millimeters of mercury. If we follow that up right here, we can see that we're about 75% saturated. So what that means is even at our lowest oxygen partial pressures in our tissues, where the cells are using up oxygen at a pretty quick pace, we are only 75% saturated. So what that means, if I were to go up here, oops, I would still have, that is not the right color. Let's see if I didn't mean to erase my hemoglobin. So I would still have 3 out of the 4 spots bound to oxygen. So I'd still have 75% of my hemoglobin would be bound to oxygen. I'm losing 25% by the time I get to my tissues. And then that blood in the peripheral, right? So we come back to the heart, we go out to the lungs, we pick up that remaining oxygen molecule to get us back up close to 100%. So this is what we're dealing with on a normal basis. Now, when you start getting a little bit lower, so when we're heading in this direction here and your partial pressures of oxygen decrease, look at how rapidly that saturation curve drops off. So here, our slope is kind of more like this compared to lower than 40%, our slope is way steeper. And that is the chemical properties of hemoglobin itself. So you might be reading in the book a little bit, or maybe back in chapter 19. As oxygen binds to hemoglobin, it changes its shape a little bit and it allows it to have more oxygen bound to it as you are close to high oxygen concentrations. When you take that hemoglobin molecule and put it in areas of lower concentration, you will lose your, one of your oxygens, and that changes the shape of the hemoglobin, and it makes it easier for the other oxygen molecules to unbind from the hemoglobin. So it's right around this point here that the remaining oxygens really pop off a lot quicker than this first, losing of one or two of those first oxygens. Okay, so this is our baseline oxygen transport hemoglobin saturation curve. If we look at some conditions that are outside of normal, we can see how those can be affected. So this is going to take a look at kind of a similar idea of these hemoglobin saturation curves and differences in pH and differences in temperature. So when we take a look at pH, our average blood pH is 7.4. So that's this purple line here. So this is normal, this guy right here, 7.4. And so that's going to follow our, if we're going to look at our normal values, that's going to be our 40 and 100. So again, we're at like 97 here, and we're about 75 here. Now, let's say you might be a diabetic or some kind of acidosis, lactic acidosis, ketoacidosis, something's happening to make your pH lower. So you're on the more acidic side. So that's going to be the blue line here. So if we take a look at the blue line, this guy right here, and follow that along, okay. Let's take a look at what happens at those same PO2 levels. So if we were going to take a look at the PO2 here and here, we're going to see quite a bit different numbers. So here, if we're going to kind of trying to look at the graph, so this might be more like an 86 maybe partial pressure, or no, this was percent saturation. Okay, but down here at the tissues, we are going to be, it looks like more like 60%. So when you are in an acidic condition, what happens is your hemoglobin doesn't hold on to the oxygen as readily. So even in the highest concentration of oxygen right there at your lungs, you're only going to be about 80% saturated, 86, 85% saturated. So you're starting off with lower saturation to begin with. And then when you get to your tissues, it kind of gives up that oxygen a little bit easier. And so that by the time you get to your tissues, you might be at 60% saturated instead of 75% saturated like you would in a normal pH. All right, so this is what we call the Bohr effect, is when we have an acidic condition. When we take a look at the alkaline, so that's this red line here, right, the alkaline 7.6, take a look at our spots here, kind of keeping track of these two values. So here and here. So if we have an alkaline condition, so this could be metabolic alkalosis or respiratory alkalosis, at 100 partial pressure, we are, looks like pretty close to 100% saturated. Hey, that's pretty good, right? We are even higher than we would be at normal. But take a look at what happens out at your tissues. We're now probably about like 80, maybe it looks like 84%, kind of guessing on that. So what's the problem with that? When our body is used to getting, say 25% of the oxygen delivered into our tissues, here comes my cat. When we're used to getting 25% of the oxygen dropped off, when we're in an alkaline condition, that changes the hemoglobin, makes it hold on to the oxygen a little bit tighter, which is great at the lungs. We can load up on 100% saturation. But then when we get to the tissues, it's not letting it go quite as well. And so the blood leaves the tissues without dropping off all of its, all the oxygen it normally would, so like at the 75% if we are at a normal pH. So either side of this pH imbalance is not good for your tissues. Either you're not bringing enough oxygen to your tissues to begin with, or you are bringing a lot of oxygen to your tissues, but the hemoglobin won't let go because of that alkaline condition. So those are the effects of pH changes on this hemoglobin saturation curve. Now, if we were to take a look at temperature, we can kind of see some similarities. So our normal body temperature is 38 degrees. And so that orange line, that's our normal hemoglobin saturation curve. So we had 100 partial pressure, we're about 97% saturated. At 40 partial pressure, we're about that 75% saturated. Now let's take a look at if you have a fever, like a really high fever. This is similar to an acidic condition where at 100% or 100 partial pressure and 40 partial pressure, let's get those numbers in here. So this looks to be on the graph maybe like 85. Oops, I'm still in highlighter mode. This is like an 85% saturated at the lungs. And then down here, maybe looks like it's 55. Yikes. So in higher temperature situations, like in a really high severe fever or hyperthermia, you're not going to be able to pick up as much oxygen at the lungs. So then you're going to have less oxygen to drop off at your tissues, 55%, which is pretty darn low. And then if we take a look at our cold temperatures, right? So 20 degrees is like pretty darn cold. We don't even get, we reach 100% at like 40 partial pressure. So I'm just going to start here. So if we take a look, that's kind of a purple color, right? So let me get my little purple pen. And so we are, looks like 95%. So this at 40, so this is at your tissues. So always kind of connect 40 partial pressure of oxygen with the situation that's happening in your tissues. Our hemoglobin is still like 95% saturated. So it's picking up a lot if you have oxygen to bring into your lungs at 20 degrees. So this oxygen is coming in, it's really holding tightly to the hemoglobin, but by the time it gets to your tissues, it's still holding on to the oxygen. The hemoglobin is holding on very tightly and it won't let go. So your tissues are not getting the oxygen that they need. And even here at the 10 degrees Celsius, so if we highlight that value, the 10 degrees Celsius is really high. We're still at like 95% saturated at a 20 partial pressure, which is, I mean, you can't survive obviously at these lower temperatures, but it just kind of shows you the extreme, if you lower the temperature, that's going to make hemoglobin hold on much tighter to that oxygen. Now, this has some benefit in therapeutic realms, because a lot of times you hear the stories of like kids a lot of times crashing through ice on a lake and they're underwater for a long period of time, longer than they would have survived normally, but they're able to be revived. Or heart attack patients or stroke patients being put into cold environments and actually cooling their blood through a bypass machine, reducing the damage of the stroke or the heart attack. Is because when you cool down the body, not only are you keeping the oxygen bound to your hemoglobin, but you're slowing down the metabolism, the oxygen demand, so tissues can survive with the small 5, 10, or 15% oxygen that can be released at the peripheral tissues because their metabolic rates are a lot lower. So that's kind of a clinical application there of the temperature and hemoglobin curve. Okay, so that is our hemoglobin and pH, hemoglobin and temperature. We talked about that. All right, so when we are going to take a look at oxygen, oh, and then I forgot, fetal hemoglobin. Remember when we were talking about fetal hemoglobin in the blood chapter, and we're saying how it stripped the oxygen away from mom's hemoglobin? Well, there's the curve for you. So at these partial pressures, right, at the tissues, there's mom's saturation curve, there's baby saturation curve. So at the peripheral tissues, at that exchange, at the placenta, baby's hemoglobin wants to be 90% saturated and mom's is only about 75%. So baby's hemoglobin steals oxygen from mommy's hemoglobin. Okay, so here is actually what is happening at that respiratory membrane in your lungs and at your peripheral tissue capillary beds. So we're going to start at our pickup, so oxygen pickup. We'll start here first. So this was our 100 partial pressure in the alveoli as we are breathing in, that oxygen is moving into our blood. Now, there's a couple places that this oxygen goes once it goes into your capillary. A very small percentage, I gotta look at my notes here. A very small percentage, I wanna say like 3%, I'll just say 3%, I don't have the stats in my notes. About 3% of this oxygen goes directly saturated into the plasma, just like because, you know, Henry's law, it's soluble in liquids. So about 3% goes into your plasma, just carried in the watery part of your blood. The other 97% goes into the red blood cells, diffuses through the red blood cells and binds to the hemoglobin. And this is what we call oxyhemoglobin. So like 97% of all the oxygen that moves into your capillaries is carried by the hemoglobin. And what's cool about this is it's reversible. So here is that pickup of oxygen at the lungs. And then remember when we were in the blood, the peripheral capillaries, we went down to that 95% because of the venous drainage in your lung tissue. So here we are now going towards our 40 partial, I should say partial pressure. This is not percent. Okay, our partial pressure. So that's our diffusion, our concentration gradient. And all that happens is that 3% just diffuses straight out. And then our oxyhemoglobin, the oxygen molecules just pop off. They just pop off of the hemoglobin and exit following that concentration gradient. And so then that is our oxygen delivery. So that's really easy. It's just split into those two categories. A tiny percentage, 3%, is dissolved in the plasma. A larger percent, the 97%, is bound to hemoglobin. Pretty easy. It's picked up at the lungs, dropped off at the peripheral tissues. Okay. Now, CO2 is a little bit more complex. And the reason why is there's a couple reasons why, is because CO2 is soluble, a little bit more soluble in the blood plasma. So here we are going to see there's 7% of CO2 is dissolved in the plasma, where it was only 3% soluble in the oxygen when the oxygen was picked up. So then of that remaining 93% of the carbon dioxide that gets picked up at the tissues, it goes into even two more pathways. 23% of it binds to hemoglobin, and I'll talk about that in a second. And then we have 70%, so the big majority of carbon dioxide doesn't even transfer as carbon dioxide, it gets converted into something else. So I wanted to, let's talk about this carbaminohemoglobin for a second. So remember, I will draw my little hemoglobin molecules, right? These little proteins, alpha, beta chains. And then we had our heme unit in the middle. That's where the oxygen binds. So the CO2 does not compete with the heme. The CO2 would be binding out here on the amino acid chains of the hemoglobin molecule. So that's why it's called carbaminohemoglobin, because the carbon dioxide is bound to the amino acid chains of the protein, not the heme unit. That's not competitive. But there is another closely related molecule that is competitive for the oxygen site, and that's carbon monoxide. So CO, carbon monoxide, does compete on that heme unit. So if you get carbon monoxide poisoning, that binds irreversibly or very, very tightly, way stronger than oxygen, and it does not allow oxygen to bind to that heme unit, and so you suffocate, you die. Basically, that's carbon monoxide poisoning, is because the carbon monoxide kicks off the oxygen, binds to your hemoglobin, does not allow oxygen to be carried to your tissues, and you basically suffocate all your tissues. You die. All right. So that's our carbaminohemoglobin. So both of those, or the first two things, are pretty straightforward. So that 7% stays as carbon dioxide dissolved in the blood plasma. 23% is bound to the amino acid chains of the hemoglobin, carbaminohemoglobin. The other 70%, this is where it gets a little bit trickier. So inside of the red blood cell, we have carbon dioxide mixing, right? Here's carbon dioxide mixing with water, plus it's a chemical equation. And there's an enzyme that's located inside of red blood cells called carbonic anhydrase, this guy right here. And it produces carbonic acid. Oh, I don't have it written here. So this is carbonic acid. Okay, so that's one part of it. So then there's another half to this equation. This carbonic acid breaks apart. It's called dissociates. It breaks apart into a hydrogen ion, and this ion here called bicarbonate ion. I'm just going to call it bicarb for short. And if you'll notice, the carbonic acid has an H2, CO3, and then when it breaks up, it loses one of those H's as a hydrogen ion. So that's the H plus, and then the other H, the HCO3 minus. That bicarb is a negatively charged ion. A hydrogen ion is a positively charged ion, so it's like an ionic compound. All right, so now we're inside the red blood cell. We've created a bicarb, and we've created a hydrogen. Now, we don't necessarily want to keep these things inside the red blood cell. First of all, if you increase the concentration of hydrogen ions, you do what to the pH? You decrease the pH, it becomes acidic. So you don't want that. You don't want the insides of your red blood cells to be acidic. So there's other proteins, there's protein buffers in your red blood cell, and oh, that hemoglobin, it also does another job. Let me see if I can get a different color here. I'll do purple. So it actually buffers some of these hydrogen ions. So not only is this hemoglobin carrying some carbon dioxide, it is also buffering some of this hydrogen that's being given off by the breakdown of carbonic acid. All right, so we've taken care of the hydrogen. It's not changing the pH inside of our cell. And now what are we going to do with this bicarb, this HCO3 minus? Well, it also can't stay inside of the red blood cell. So there are little exchange protein pumps on the plasma membrane of the red blood cell, and it is a direct exchange for one molecule of bicarb is exchanged for one ion of chlorine, right? Because we want to maintain our electrochemical gradient. So if you're losing a negative charge, you want to be balanced with a negative charge. So this whole exchange process is what's called the chloride shift. So all the chloride shift is that bicarbonate ion, the bicarb that's produced after this whole equation, gets kicked out of the red blood cell and a chlorine goes in for this short little ride from your peripheral tissues back up to the capillaries in your lungs, because we're going to reverse it all by the time we get there. All right, so let's take a look at what happens. We'll see this again on my slide. So what we just did here is the pickup. Right, carbon dioxide pickup. Here's that 45 partial pressure in the tissues, and in the blood was 40, right? So this is going to be our concentration gradient. So if you remember, if we break down 100% of the CO2 that's coming in, 7 was dissolved as plasma. 23 is bound to hemoglobin, carbaminohemoglobin, and then 70% was converted into the bicarbonate ion and the hydrogen ion. So this is our carbonic anhydrase reaction, right? So water plus the CO2 that's coming in creates the carbonic acid. The carbonic acid splits into the hydrogen ions and the bicarb. The hydrogen ion is buffered by the hemoglobin. The bicarb is kicked out while a chlorine moves in. That's our chloride shift. So this is what's happening at your tissues. So this is our peripheral tissues. Carbon dioxide pickup. So this is how CO2 is traveled. The majority of CO2 is carried from our peripheral tissues to our pulmonary capillaries, not even as carbon dioxide. Just 7% of it is carbon dioxide in the plasma. 23% is carbon dioxide hooked to a hemoglobin molecule. So 70% of carbon dioxide that we make in our tissues doesn't even stay as carbon dioxide as it's traveling back to our body and out to our lungs to then reverse everything we just did. And I will tell you, there is a reason for this. It's not just some crazy stuff to make it hard for A&P students to understand carbon dioxide transport. That buffer, this HCO3 is super important in maintaining our blood pH. We're going to see that when we get to the kidney and the fluid electrolyte acid-base balance chapter. It is super important, and that's probably why it's doing this. It's not an accident. So, all right, so let's say we're coming back to our, let's see where we're at. So coming back to our body, from our body to our heart, out to our lungs, we are ready to drop off that carbon dioxide. So this was our 45 partial pressure in the capillaries and our 40 partial pressure in the alveoli. That's our concentration gradient. So the CO2 is driving all of this reversing of this reaction. So again, here's our 7% that was in the plasma, just diffuses straight out into the capillary. The 23% that was hooked to our hemoglobin pops off of the hemoglobin and just diffuses into the alveoli. Now here's just the reverse of everything we did at the tissues. So all of the buffer, this HCO3, this bicarbonate ion, comes back into the red blood cell, kicks out that chloride. So it's like a reverse chloride shift. The hydrogen that was buffered by the hemoglobin binds to that bicarb, produces carbonic acid. The carbonic acid breaks off into water and CO2, and then the CO2 diffuses into the alveoli. And then that is our exhaled air that is higher in CO2 than our tissues. So carbon dioxide pickup delivery, I know it's a little bit more challenging. I really encourage you to try to get comfortable with this equation. I'm going to write it down here because you're going to see it a lot. So know that CO2 plus water gives you carbonic acid, H2CO3, whoops, that then dissociates into hydrogen ions and bicarb ions. So this is the direction that happens at our tissues, okay? Then when we're at the lungs and we go to drop off, it is just reversible. So bicarb plus hydrogen ions become carbonic acid, which dissociate into water and carbon dioxide. And so this is how we breathe out. So the directionality going this way is at the tissues. And when we drive it this way, we are at the lungs. Okay, so again, I strongly encourage you to be comfortable, start getting comfortable with this equation. It's called the carbonic acid bicarbonate buffer equation. Now that's a mouthful. Bicarbonate, nope, that's not right. Carbonic acid bicarbonate buffer equation or system. So we're probably going to see this at least 4 more times in the course of the rest of this term. We're going to see it in the digestive system. We're going to see it in the urinary system, and we're going to see it in the fluid electrolyte balance chapter. I said 4, maybe 3. All right, so I think that's the end of, yes, so that's the end of this little mini lesson talking about gas transport. So how oxygen is carried from the lungs to the tissues and how CO2 is carried from the tissues to the lungs. We have one more mini lesson on the regulation and control of respiration. I will see you next time. Bye.